Also, tell me all the videos which I have not shared with you. I mean, many I have missed.
Yes, sir. Sir, I'll just check it after the lecture and
Yeah.
I'll send you in the voice message, sir.
Yes. Okay. So we'll continue doing some more programs. Then we go to the next concept. So, field on the charge. Okay. So now dipole moment. Okay, we were doing the dipole moment and angular momentum relation, right?
Yes.
So the last was the disk problem, right? That we solved. Imagine if you have an annular disk, a disk which is having a cavity. The inner radius is A, outer radius is B. And it is uniformly charged. And if we spin this disk with the angular velocity omega, and the sigma is the surface charge density. So there are two questions that you need to solve. First is, what is the magnetic field at O? And second, what is the dipole moment of this rotating disk? Okay. So try one by one. I think we have done the BO part, no?
So,
This part we have done, BO.
sir, no, sir. I guess we have only done for the big, like the full disk, sir.
Okay. Fine. So do it for this, okay?
Okay, sir. Sir, can you just come back in a minute?
Yeah, sure.
Sir,
Yes.
yes, sir. Sir, I'm getting the B naught value as uh, mu naught sigma omega B minus A by 2.
Okay. And what is PM?
Sir, PM value I'm getting as pi sigma omega B power 4 minus A power 4 by 4.
Like this, right?
Yes, sir.
I think that should be the right answer. Let me just confirm. So dB equals to sigma 2 pi r dr q omega by 2 pi into pi r square, right?
Yes, sir.
Yeah, that's correct. That is also correct only. Very good. So for any given charge distribution, if it is rotating charge, then you can always have the dipole moment, and we can also calculate the magnetic field. So if I take a ring, I think we have done this part. And if the ring is rotated like this, and if you wish to find the magnetic field at a distance x, and the radius of the ring we are going to take as r. So what will be the b at p? So we have the formula, if you remember, mu naught by 2 n I, so n is 1, n I r square by x square plus r square power 3 by 2.
Yes, sir.
The only thing is to replace I, right?
Yes.
So I becomes q omega. Let's say this is okay. So BP turns out to be mu naught by 4 pi uh, q omega r square. So every question of a BITSAT law which we have derived can also be derived the moment we go this particular way, right?
Yes, sir.
Okay. And one more thing that I would like to highlight here. Okay. Okay. Just let me check if we have missed something. Okay, so we are done with everything. So we can go to the next concept that's called ampere circuit law. So there are many variants of this. So we have Maxwell Ampere circuit law. Right now we are going to only study the Ampere circuit law. And this law is analogous to the Gauss law of electrostatics. So we can say that in short, we're at ACL. Ampere circuit law is analogous to the Gauss law of electrostatics. So what this says that mathematically the line integral over any closed contour or loop is always equals to mu naught times I enclosed. So what we write here is the circle is called, in this context we call line integral So because we know that by nature of B, the B is always like a loop. If you recall, so any source of current creating the magnetic field will create a loop. Okay. And because every so every current carrying wire will create a loop shape of magnetic field. So magnetic field always encloses in a line. Okay, so it will have a closed path. So we call it contour. So for every contour, if you calculate the B over the perimeter of contour, so if you calculate B dot dl, so you will take a dl, you will check the B at that location, you will take the dot product. So if you do all these things, eventually this will give you the answer mu naught into I enclosed. Now similar to electrostatic, what E represents? So if you remember, E represents the resultant electric field at that point of space. Similarly, in the Ampere circuit law, the B represents the resultant magnetic field induction at the point. So B is called resultant magnetic field induction. Okay. So resultant magnetic field induction means it is not the field of a current carrying segment. Rather, it is the resultant field of the point in space, similar to the electrostatic definition. So if I do some random loop of any shape, and then If you talk about the current carrying, just so let's say we have a loop. This loop is a hypothetical loop. It's not physical loop. Okay? Imagine if I draw this loop mentally. So imagine if I draw the loop mentally. How many times? This is better. Then this is enclosing like a how many current carrying wire is crossing this loop. Let's say there are many wire which is crossing this cross section. So you can see there are many current which is coming from one side and going to the other side. Now these circuits are not shown completely, just the part which is intercepting this loop I have shown here. And every wire might be carrying some current, so it's called I1. So when we say that B dot DL, because there are many wire, so every wire will have some magnetic field induction, right? So all will contribute something here. So if I choose a random point P, then at this point P, how many field will superimpose? So not just 5, which you see, rather it will be imposed by the entire circuit of all the 5 loop. Every current is a part of some circuit, isn't it? I1 is a part of some circuit, I2 is a part of some circuit, I3 is a part of some circuit, I4 is a part of some circuit, and I5 is also part of some circuit. Okay. If every wire is representing some current in a circuit, then the net magnetic field at point P will be due to 5 circuits, right? Assuming that there is no other circuit in the vicinity. So if I draw a single current is also here I6, and let's say I6. Now how many circuit will contribute at point P? 5 or 7? Pardon? No, when I say contribution, it means who can create field at point P? Who can? I think everyone.
Oh, yes.
So when I say who will contribute, it means everyone. Who, see, if the property of a current carrying wire is to create field, then everyone is eligible to create, right?
At the particular point where the loop you
Yeah.
have drawn it.
Yeah.
Yes.
So you can choose any random point in space. For that matter, every point of space will have contribution for every current carrying loop, isn't it?
Yes.
Not only restricted to what I have drawn. And the contour which I have drawn is the imaginary contour. This is imaginary contour. Imaginary contour. And in a technical term, we call this as empyrean loop. Okay. So this B represents the B due to every possible contribution in the universe. In fact, I have shown 7. It may be infinite, which I haven't shown. So technically, the B refers to the resultant B, and the B will take the contribution for everyone in the universe, every current source in the universe will be responsible for contributing some B there. So using the principle of superposition, the resultant field. Yes. Just understood. So
Yes.
every current source will contribute, and it is not about one particular source. The contour I am drawing arbitrarily. Okay? This is what I chose to draw. And when I draw, then I can see some of the wire is passing through that contour. So you can say contour creates a surface, right?
Yes.
So it is similar to the flux. So you can say that a wire crossing the contour is like creating a flux. So it is like we are trying to understand that what is the current flux, the flux of current. Okay. And similar to the formula Q upon epsilon naught, we call it flux. Mu naught into I enclosed, you can call, or you can think logically as a current flux. So flux will only decide like who is crossing through it, because others are not going. So what is the flux of other? Can we say 0? So for I6 and I7, are they contributing in terms of magnetic flux? The answer is no. I6 and I7 are not creating the magnetic flux through the loop, isn't it?
Yes, sir.
I think you're not getting confused.
Yes, sir. I'm slightly getting confused. Sir, when you said that, like all the currents are contributing to the field, that
Yeah,
was
they are creating to the field, but not to the flux. Do you remember field and flux relation?
sir, I'm not really conceptually understanding it. Sir.
So let's cover the loop and make a surface. Okay. And if you remember that in electrostatics, if we have a charge outside, then it will have the field lines which is entering and exiting both. So any charge which is outside will not contribute in the net flux, right? But it
Yes,
will definitely contribute in the field, isn't it?
yes. Sir. Oh, okay. Yes,
So field contribution is not the criteria that it must have the flux contribution.
yes.
Okay. Similarly here, at any point on the contour, the B will have the contribution of field. I mean, sorry, every current source will have the contribution of field, but every will not have the contribution of flux. So who will create the flux is the one which passes through this surface. And which surface? The surface enclosed by the contour. Okay.
Mm,
Now, what is the meaning of contour? So let me tell you the other meaning. Contour is defined for open surfaces. So let's say if you have a polyethylene bag, which you call polythene, if you go and buy up some sort of packet, and then you can see this is the opening. So the red line is called contour. Understood?
yes. Sir.
So any open surface will have the opening, and the opening, if you raise the opening only, what you get is called contour. So basically contour is defined for open surfaces. So can we have contour for closed surface? No. Because when we have closed surface, we cannot define contours. Contour is the idea. So contour means any closed loop, and it is the like edge. You're trying to find the edge of a surface, okay, which is open surface. So I can take a flat surface as well. So even a flat surface will have contour, yes or no?
Yes, sir.
Because flat surface is anyway open surface.
Yes, sir.
So contour will be there also. You can create a hemispherical surface. Okay. So the whole idea is that every surface will have the edges, and that edge is called contour. Understand?
Sir, and the surface is supposed to be
Open.
imaginary.
Yeah, yeah, yeah. Imaginary,
Imaginary.
imaginary. Yeah, everything is imaginary.
Okay, sir.
For any imaginary surface which you draw, there is a contour concept. Okay.
Yes.
So, for example, let's say if you talk about the Earth, okay. So you must have seen the globe, right?
Yes, sir.
Now, if you draw the contour of any country, let's say if you're drawing the contour of Africa, is it Africa on a flat surface or curved surface?
So it's actually a curved surface.
So it is like a three-dimensional contour, no?
Mm,
So the
yes.
contour is part of this curved land actually.
Yes,
Okay.
sir.
So contour is not supposed to be flat. Contour is an idea, which means if you take a part of a surface, it is if you take a closed surface and if you take a small piece of it, so every piece of every part of a curved surface, closed surface is open surface, right?
Yes, sir.
A part cannot be closed, no? If the full is closed, part is open, and then the edges will be the contour. Okay, the edges will be the contour. Understood?
Yes, sir.
So that is the whole idea of contour. So what this law is saying, that similar to the Gauss law, if I have a charge here, then flux lines will cut like this, correct? In case of current carrying wire, if the wire is crossing the surface, let's say if you have a wire which is crossing like this, so it's coming out of this. So because just a minute. Okay. No. So you understood the idea of contour,
Yes.
and because we have contour, so then there is idea of flux also.
Yes.
Now the flux we have to think in terms of current actually. Okay. Now in case of contour, there are some rules. Like in earlier case, the flux means uh, what is going one way, what is going other way. So if one way we take as positive, the other way will be negative flux, right? So
Yes.
if all are going this way, if I call these are positive flux, then if someone will enter from here and exit from here, then if these are positive, then these are negative.
Yes.
Or if these are negative, then these are positive. So what we can realize that there are two possibilities, and that's the source of confusion. Like how to take the direction and say one as positive and say other as negative. Just understood. So if I have see the ambiguity here, so there must be some way to remove the ambiguity. Okay. And so
Determining what is positive and what is negative.
yeah, right. So for that, Ampere proposed the sign convention. So what he said that in the LHS formula of Ampere circuit law, which says B dot DL, the DL represents the length of the contour. Okay. But the question is how to understand the direction of length. DL cannot have the direction until we assign it. DL is simply the length of the contour, then it will not have a direction on its own, isn't it?
Yes.
So first of all, it is hypothetical. Second is I am saying this is DL. So DL cannot claim the direction, but what we say that we decide to traverse the contour. So you will choose how to traverse it. So let's say I'm trying to traverse this way. So the arrow is representing what? Direction in which we want to traverse the contour. Okay. And if the direction is okay, direction in which we want to traverse contour will give direction to DL. So DL is a length, but DL vector is the sense in which you traverse. So let's say if I'm traversing this sense, so we can take the right hand rule, and if you take the curls of the finger as per the traversing direction, the thumb will give you the positive direction. So for this loop, the positive will be upward. So below will be negative. Is this clear? Is this part clear?
Yes.
So you have to use the right hand rule. So take your right hand and try to take the curl of the finger along the loop. So try to hold the curl with your finger. How the thumb is pointing.
Sir, so okay. Yes, sir.
So you got the idea?
Yes, sir. Sir, so we actually know like in which direction the current is going. So we keep it like that and we curl the finger. along the route.
No, we choose the direction to traverse.
Okay. So in that direction, we consider wherever our thumb is pointing as positive and the opposite as negative.
Correct. Very good. So, so let's say if we see, first of all, the choice of the traversing is up to us. So we choose. It's not like someone else will come for us. And why it is important? Because DL cannot have its own sense, right?
Yes, sir.
So DL will get only sense when we give the sense, and therefore we need to choose that how I'm going to traverse the loop. And the moment I decide how to traverse the loop, which I chose, then the DL will get its direction, and therefore the positive and the negative direction will also be assigned accordingly. Okay.
Yes, sir.
So if I have a loop, a same loop, and if I choose to traverse in the reverse, this, then the DL vector will become this way. And therefore, if you take the right hand, you can see the positive will be below. So any, I mean, this is the positive direction and this is the negative direction. So this is how we assign the positive and negative current direction. Okay. So if the current is going upward, it is negative current, and if it is going downward, it is positive current. In the previous case, the any current which is leaving on the upper side is a positive current, and anything which is leaving or going to the lower side, it's a negative current. So that is how the current direction will get its sign assigned. Is this clear?
Yes, sir.
So in many situations, we cannot calculate B dot DL because we don't know the B value exactly. So let's say you don't know B, but the B dot DL can be calculated. So we don't know B individually, but because this is the formula mu naught into I enclosed, so we can do this. So let's say if we have a loop like this, now this is the Amperian loop. If this is the Amperian loop, and I choose to move this way. So now you know that the DL will get what sense. And now we have some current carrying wires. Let me give the direction. I1, I2, I4. So when I say current enclosed, it means the one which crosses the surface whose contour is shown to you. So you don't know the surface, what you do, what you see is the contour of the surface, right?
Yes, sir.
So how many surface we can create? Infinite.
Yes, sir.
For a given contour, how many surfaces are possible? Infinite, isn't it?
Yes, sir.
So if this is the contour, I can draw either like this surface, I can do this surface. So there are infinite possibilities. So let's say if I draw a big contour, you can see this current, the I6 will also come, right? But you can see
Yes,
I6 will enter the contour and leave the contour both, right? So anyway, contribution is 0. Okay, understood.
yes, sir.
So even if you try to extend the surface by bulging outside, the one which is not contributing will never contribute, no matter what. So any possibility of drawing of contour, I mean the surface whose contour is given, will never change the answer. It's clear.
Yes, sir.
So if I try to calculate the B dot DL, the net value, of course, it is impossible to get the B in such situation, but we can say this must be equals to, as per the traversal direction, which are positive current and which are negative current.
I1, I2, I3. Yes, sir.
And then 4 and 5 are negative, right?
Negative. Yes, sir.
So if we just solve the same question with reverse direction of traversing, the sign of I1, I2, I3 becomes negative and the rest will become positive, right?
Yes, sir.
And why this will give you the same answer? Because see, once you reverse the direction, the B dot DL will also reverse, isn't it?
Yes, sir.
If B dot DL is giving you positive answer in one case, it will automatically give you negative in the other case,
Yes, sir.
isn't it? No.
Yes, sir. Sir,
Let's say B is like this at some point, and this is a DL. So if you go towards the right, the B dot DL will be positive answer.
yes, sir. Okay.
But
Yes,
if you go left, it will become minus B dot DL, B DL cos theta,
yes,
right? So by changing the direction of traversing, what happens? We always get two different sign as well.
yes,
So it really doesn't matter which way you move, because the LHS will always adjust its value accordingly. Is this clear?
yes, sir.
So before we solve a general question, we'll solve something more first here. So there is a very nice problem that we need to understand. Just a minute, I'm searching for it. Yeah, I'm just searching. The name of this is just.
Sir, can you just come back in a minute?
Yeah, please. Yeah.
Yes, sir.
Just a minute. So I've sent the sheet actually. Now I got the sheet actually. Actually, the name of the sheet was different from what I was trying to search.
Okay, sir.
Okay, so now you can see question number 6, which I have again sent separately. So you have to read this question and to think about this question and to think about some symmetricity and so on, and try to solve this. Try to think for a while, then I'll solve.
So what does this Tesla meter exactly measure? I don't
It's
understand.
a B dot DL, because B is in Tesla and DL is meter.
Yes, sir.
So that is the unit of B dot DL. It means, okay, let me help you out. So what is given is a rectangular loop. This is the contour actually.
Okay, sir. So just an imaginary reference.
Yeah. So this is the imaginary rectangle, and therefore we can name it A, B, C, D.
Sir,
Okay.
the points are different, so B comes down.
Okay, right. This is fine.
Yes.
Now we have two types of current direction. So one is here, which is cross current. Another is here, which is dot current.
Yes.
And the distances, so these are symmetrically located, which is X and Y. So very much both are symmetrical, right?
Yes, sir.
And the direction of traversing is given to you like this. I think you can see it. Current is also given.
Yes, sir.
Okay, so that's a thing given. What else is given is, let it be. Oh. The BQ means the magnetic field contribution due to this wire. This is BQ, and BP is the contribution due to the. So at every point, how to write the B dot DL? If you write the B dot DL, B dot DL equals to mu naught. Now the B we can write due to the B due to P plus B due to Q, because we have two wires, right?
Yes, sir.
As per the direction of traversing, you can clearly see the outward is what? 2I.
Yes, sir.
Inward is I. So net is how much?
Sir, I.
So I write as 2I minus I, right?
Yes.
And now I can divide this part BP dot DL plus BQ dot DL. Okay.
Yes, sir.
The next thing is, every loop will have 4 paths. So we can write this as 4 times. BP dot DL A to B, BP dot DL B to C, C to D, and D to A. Similarly, we can do it for the Q as well, right?
Yes, sir.
So we can write as A to B, BQ dot DL, B to C, BQ dot DL, C to D, BQ dot DL, and then D to A, BQ dot. And that is equals to mu naught I. Now the question is, we are supposed to substitute every value. Let's see what is given to you. BQ dot DL from A to B is 2 mu. So BQ dot DL, oh, this is given 2 mu naught, right? You can see, isn't
Yes,
it? Now if B Q dot dl from A to B. A to B is here and Q is here, is 2 mu naught. We can use the symmetric property. So what will be the BP C to D? It is like this. If this creates BQ dot DL from A to B as 2 mu naught, what do you expect this will create here?
minus
No, how much this will create? It is symmetrical. This distance and this distance are same, right?
opposite. So it will be mu naught.
Mu naught, because it's half current, right?
Yes, sir.
So if this is creating 2 mu naught here, this will create mu naught or plus or minus.
So just a second, sir. It will be
It will
so it
be
will create plus, sir.
it will be like this. You see, it will create a field like this, no?
Yes, sir.
The field will be opposite to the direction of C to D, right?
Yes, sir. So it will be
Minus.
minus.
So what we
Sir,
have?
I initially said minus.
Oh, you said minus. Oh, sorry. So I didn't hear. So actually, what we have to do is we have to write the pairwise answer, whatever they have given. From there, we have to create the pair. So if given is A to B, BQ dot DL is 2 mu naught, so you can always write C to D BP dot DL minus mu naught. Okay, so one pair, one answer. And you can see there are 3 pair given answers. So actually, you can find all answers. Okay. Now, next pair. What is given is D to A. Oh, you can see D to A, right?
Yes.
BP dot DL is minus 2 naught. I can directly write BQ dot DL for D to A will be how much? First of all, it will be double and opposite sign. Current
Yes.
is double, so double and opposite sign, which is 4 mu naught, isn't it?
Yes, sir.
Okay, so that's the answer. And I think A to D and B to C will have similar thing, right?
Yes, sir.
Because they're symmetrical, no? So even that is same for the C to D. Now last is DP A to B is minus B naught, A to B. So if BP A to B is minus B naught, then BQ C to D will be plus 2 mu naught.
Yes, sir.
So after writing all this pairwise, we can actually substitute every value. So you see, BP A to B is how much? BP A to B is minus mu naught, right?
Yes, sir.
So BP B to C is how much? B to C. So what is given to you? BP C to D is given minus mu naught. So I think that is same for B to C also. No, C to D. Wait a minute. BP D to A is minus 2 mu naught. So whatever is D to A is same to B to C, isn't it?
Yes, sir.
B to C is same as D to A. And both will
So,
be
but yes, sir. Same sign.
same. Minus 2 mu naught. Minus 2 mu naught. And BP C to D, we have written somewhere. BP C to D, yeah. Minus mu naught. And let's come to here. BQ given BQ B to C. BQ B2C, B2C. Yeah, that's same as D2A.
Yeah. Yes, sir.
BQ, yeah, BQ D2A is 4 minutes, right?
Yes, sir.
This is also going to be 4 minutes, right?
Yes, sir.
And C to D, BQ C to D. Yeah, it's 2 minutes. And BQ D2A, 4 minutes, right?
Yes, sir.
So you can see if you add minus 1, -3, -4, -6, -6 is this side, and here 2, 6, 8, 2, 6, 8, 12. So
Yes,
minus
sir.
6 plus 12 is how much?
6.
And this is equals to how much we got minute into I?
Yes, sir.
So this is a very challenging problem because you have to think of a lot of symmetricity and contribution, and then only you can get the answer. Okay.
Yes, sir.
All right. So this is just to understand okay, what is the meaning of contour and how we actually write the equation. And here you can see the B will have only just two contribution. They are just two contributors, so that's why it is easy to interpret. Now, similar to the electric flux, I mean Gauss law. In Gauss law, we used to draw the Gaussian surface, and if you remember, we used to draw the Gaussian surface as per the nature of electric field that we were knowing already. So similarly, in case of Amperian loop, first we need to analyze the direction of magnetic field lines, and we'll try to draw the Amperian loop such that the B dot dl becomes mathematically feasible to calculate. Okay.
Yes, sir.
So the loop will also have a very natural choice that we'll see. There is no fixed method, but given a context, we can easily figure out that which kind of loop will be most suitable.
Yes.
So first of all, we'll try to understand that what we can do and what we cannot do. So Gauss, this Ampere law is pretty much valid every instant. It is valid for AC as well as DC current both. So you can apply the Ampere law for alternating current and DC current both. The only place where you cannot use the Ampere law is called when the charge distribution inside the conductor is time dependent, then we cannot use. Current is dependent, that's fine. So it is okay to have current distribution or current varying with time, that's okay. But the charge distribution inside the medium should not change. Then only we can think of Ampere circular law. That is the only validity case, but that case is not discussed even in JEE level, so that you can ignore. So what you are supposed to remember is that it is always valid except for the case when the charge distribution is not in equilibrium. So I will just mention ACL is always valid except for the case when ACL is always valid except for the case when distribution of charge in a conductor varies with time. So that's something. Now what I'm showing here is the
That
finite.
is current.
Pardon?
So, but then isn't that also just current?
No, no, no. So it's like this. Current means if I draw two cross section, whatever enter should come out. If
Yes, sir.
5 will enter, 5 will come out. But the next moment, if 10 will enter, then 10 will come out. The next moment, 15 will enter, 15 will come out. So that's the time varying current, right?
Yes, sir.
But it will not change the total charge between the two cross section, right?
Yes, sir.
If 10 will enter and 6 will come out, 4 is still inside,
Yes, sir.
which is four extra charge is being accumulated here.
Oh, so except those cases where charge accumulation is
Yeah,
not.
charge either, yeah, you're either losing the charge from your distribution or you're getting the charge from the distribution. When this happens, when this is called a non-steady state of charge distribution. So when the charge distribution becomes the function of time, then there is a issue.
Okay, sir.
So current is the rate of flow, right?
Yes, sir.
Current never gives you the idea of charge distribution, isn't it?
Yes, sir.
It only says that every cross section will encounter the same charge crossing it per unit time. So when I say time varying current, I'm not saying time varying charge. It is still the same charge distribution. Okay. You simply move slow and fast, right or left. But either moving slow or fast or moving right or left will never change the distribution part. Understood?
Yes, sir.
Okay. So next is okay. If we have a current carrying a segment which I have shown here, and when I saw a segment, it means some loop is there which is carrying the current. Because current cannot flow in a isolated connector, right? We must have a loop to establish the current, isn't it?
Yes.
So if that is the case, and if I choose a point pretty much here, which is the angle bisector, R is the distance or D is the distance, that's called D is the distance, I is the current, and the angle subtended by the end of the wire is that's called alpha and alpha. And let's say someone is thinking that okay, they can apply the Ampere law. So let's say if I draw a Gaussian, Amperian loop of same radius. Let me make this away. So let's say we have an Amperian loop. This is the Amperian loop because generally a straight conductor will create a concentric circles, right?
Yes, sir.
But do we have only straight conductor here or do we have something more also?
Sir, straight conductor. It's not exactly a straight conductor here.
It is, yeah, up to a certain extent it is straight, but it is again creating a loop. So
Yes.
definitely the BITSAT law gives you the answer due to the segment of a wire. But Ampere's circuital law cannot be used to find the magnetic field due to a segment, because segment is never complete, it is always incomplete part. And what we know that Ampere law is only used for the resultant magnetic field induction at a location instead of the magnetic field induction that we do for a segment. Okay, so the BP, the magnetic field induction at P, will have two contributors, isn't it? So one of them is the red line and other is the remaining line which I haven't shown. So for the sake of illustration, I have shown to you. So this B is a complex B because this B will have two parts. B due to the AB part plus B due to the remaining part. Understood?
Yes.
Okay. And therefore the lines of force which I have drawn, even that is incorrect. That is the lines of force that the red line will create, but not the actual lines of force we don't know. Okay. So we can divide this as into two parts. And for the given contour, what is the current influence, by the way?
So here it is ice.
Now, VAB, the segment, the magnetic field due to a segment, we can calculate using BITSAT law, right?
Yes.
And we know the answer also. What is the answer?
So mu naught by 2 pi d, sorry, 4 pi d to sin alpha. Yes.
This is a B. And okay, I have to remove this integration sign because we have done the integration mentally. So we know
Yes.
that the B is outside. What we are getting is dot DL, and the DL and B will be parallel because the way, if you look at DL here, and the B is also like this, isn't it? So the BAB will have contribution parallel to the DL, isn't it?
Yes.
And therefore the angle is 0. So DL, if you add all DL across the perimeter, what you get is perimeter. If you add DL everywhere, what you get?
The perimeter of the loop.
Which is 2 pi d.
Yes.
And then we have the B remaining dot DL, which is mu naught into I. So you can see what you are getting is mu naught I sin alpha. The rest will cancel out. Plus B remaining. So we have no idea about B remaining, so we cannot integrate this part, but we can know the entire answer is mu naught I minus mu naught I sin alpha. So the remaining contribution in the calculation of flux so B dot DL due to the remaining, we got the answer. It is mu naught I 1 minus sine alpha. Is this clear?
Yes.
Now, if the segment becomes infinitely long, what will happen? If the segment itself is infinitely long, then alpha becomes 90.
Yes, sir. So that means the remaining part's contribution will be almost
Correct.
0.
And that is the whole idea that for infinite wire, the total contribution and the contribution due to the wire itself is same, because the remaining is so far compared to the infinite that they will not create much effect compared to what effect the wire itself is creating. Therefore, in case of infinite wire, the B of the wire is the B net, and hence the Ampere's circuital law can be applied. Understood?
Yes, sir.
So we can say that for infinitely long wire, so for infinitely long wire, what happens? The B remaining dot dl becomes, so alpha is 90 degree, and if you substitute, you get 0 answer. So the Ampere circuital law we can only apply to get the B when the remaining will not contribute much compared to what we are calculating. So most of the infinite distribution will have the eligibility to use the Ampere law to get the B value. Any finite distribution should not be thought about in terms of Ampere law, or you can say that we should not think of calculating the B value using Ampere law if the current distribution is finite. So that is the first thing that we need to understand. Let me give you the formal proof of Ampere circuital law. So the law says that B dot dl is mu naught into I enclosed. So we'll take that infinite wire itself. And from Biot-Savart law, we know the answer for B, right? For infinite wire also. Okay. So now, no matter what kind of loop you do, it really doesn't matter. If you draw any loop, so let's say the B at this point. So B will be always normal to the radius, right?
Yes.
And DL will be always tangent to the contour, right? So DL and B will have some, maybe have some angle. It's called theta. So DL is the length of contour. So the corresponding arc length, like this length, will be equal to DL cos theta. Understood?
Yes, sir.
So the B dot D, if you take LHS, the B dot DL we can write as B DL cos theta, because that is the angle between them, correct? And
Yes,
B, due to the infinite current carrying wire at a distance R, we can write as mu naught I by 2 pi R, correct?
yes, sir.
So I can take mu naught I common. 2 pi also common. And what we're left with is a dl cos theta upon r. And if you look carefully, this is nothing but d theta. Because d theta is itself is arc length, which is dl cos theta by r. Right? R d theta is dl cos theta.
Yes, sir.
Okay, you can say d alpha. That's like I cannot take same, but it doesn't matter. And for the entire loop, if you add all angle, what we get? If you add all such angle, what we get? 2 pi.
Yes, sir.
And hence this gets cancelled. What you left with is mu naught I. So what we can say that, and this is the RHS. So we have proved, right,
Yes, sir.
that B dot dl is mu naught into I enclosed. So that is the enclosed also, right?
Yes, sir.
I hope this is clear.
Yes, sir.
Okay. So now we can use this formula for multiple questions. So in fact, this question I used the formula to get the proof, but the reverse is also there. So as I said that for any infinite distribution will or may employ the Ampere law, but finite we only stick to the Biot-Savart law. And the reason is when we show the finite current element, then we cannot see the overall contribution. And in the Ampere circuit law, the B which appear inside the integral, that always represents the resultant B, not individual B, right?
Yes, sir.
So there's application. So you can use it now. First, calculation of B due to infinitely long current carrying straight conductor. So calculation of B due to infinitely long current carrying a straight conductor. So if it is infinitely long, I can say that the B at the point of interest will coming from the same Y, right?
Yes.
Now, before you apply the Ampere law, you have to think of how the field lines will be, and we know the field lines will be circular. So, how the Amperian loop should be circular.
Yes.
That's the logical decision that we take always. And once you have the Amperian loop, which is matching the current, I mean, given current sense, so you can see current is upward, so we'll try to move like this because it will match the current. So I will be positive, right?
Yes.
So you what you like if the R is the distance, what you can write here? The B dot dl equals to mu naught into I equals which is I. Now you take any element and you can clearly see the B and dl are parallel, so this will become B dl cos 0. We can also claim that B is going to be same for every point because it's equidistant.
Yes.
And if you add all DL over the entire contour, what you get? Two pi r, right? Sorry.
Yes.
So B turns out to be how much? Mu naught I by. So for any infinitely straight conductor at any point r away from the wire, the r is always measured from the axis of wire, not from the surface. Okay. So r is always from where?
So why?
R is measured from axis of wire. Is this clear?
Yes.
So so we'll look for the inside the wire. Okay. So calculation of the okay, that's we'll keep the same case for infinite connector. Infinite straight inductor carrying current I uniformly distributed over the cross section of wire. So calculation will be inside wire. So infinite straight connector carrying current I uniformly distributed over the cross section of wire. Okay. So if we draw the wire, a wire may appear very thin, but however thin it may appear, it will have some cross sectional area, right? If you take a small piece of it, if you zoom out, what you see a cylinder, correct? So this is the cylindrical portion of the wire which you are looking at right now, and definitely the wire will continue infinitely. And if you look at the cross-sectional view, this we call the capital R, and the capital R will be the radius of cross-section, and this is the axis of the wire.
Can we just come back from there?
Yeah, yeah. Yes.
Yes.
So now if you further take if you zoom out the base part only, let's say if I zoom out this part, what you can see is the circular cross section. Okay, I'm just zooming to make it easier. So you can see the thin wire is actually this is the radius part, and this is R. And what you are calling current I, the current I is actually is spread over the entire cross section, not at one point, right?
Yes, sir.
And because it is spread over the entire cross section, and that is
Sort of like
uniform.
a solid cylinder infinitely long, sir.
Yeah, yeah. So it is a solid cylinder which is infinitely long. Okay. So
Yes.
we can say something called current density. And for uniform distribution, we can say current density is I upon the area.
Yes.
So for the sake of writing, let's say the current is inward. So we are going to assume the current to be inward, okay, for this view. And now we are trying to find the magnetic field induction at a point r distance away from center, or you can say from the axis. And because the current is into the plane, the B at the point will be in which sense? Clockwise, isn't
Yes.
it?
Yes, sir.
Yeah. The direction of B vector at this point will be like this. So B will have the circular loop itself. So if you write the B dot DL, the LHS part, it is again B into 2 pi r only. So the LHS you can directly write B into 2 pi r without writing anything. No need to do integration. It's B 2 pi r, right? Now the question is, what is the RHS? So RHS is mu naught into I enclosed by the loop. And how much when enclosed? Are we enclosing the full I or fraction?
Fraction of it. I R square by R square.
Correct. And now you can solve it, right? So B inside turns out to be how much? Mu naught I R by 2 pi r square, right?
Yes.
And if you look carefully, I upon pi r square we can also replace by current density.
Yes, sir.
So in terms of current density, the B as a function of R turns out to be mu naught GR by 2. Okay. Where R is less than R. So the current density term, I mean, formula is quite easy to remember. It's mu naught GR by 2. It's very famous as well. And this will also allow you to write in vector notation. That's very interesting because generally magnetic field, because field is a vector, so we can write a vector notation also. J is a vector, R is a vector. And you can see that the B is in the direction, the B is in the direction which is neither along R nor along J, isn't it? So what is the angle between B and J?
Sir, 90.
And B and R?
Also 90.
So how the BR should be represented in vector notation?
The cross product.
With excellent. So now if you apply it, so we can write this as B vector as mu naught by 2 J cross R. You can check J cross R direction. Look at that. If J is this way and R is I type this way, then J cross R will be like this. Okay. So which is the case here, because at this point B is downward, R is this way, and J is inside, right?
Yes.
So the confusion may be like a J cross R or R cross J. So you have to just draw one of the diagram and check the direction, and that will reassure that it is J cross R. Okay. So the B turns out to be J cross R, and this formula is very useful. We'll see some of the other application again. The next is the graphical part. So if we try to plot the graph of B versus R, you can see inside the conductor, the B will grow linearly with distance. So it is proportional, and outside, the moment you cross the surface, at surface you get the maximum value, but once you cross it,
Starts decreasing.
by the inversely proportional to R relation. So that's the two relation that we should remember for conductor. So the next thing is that writing the BITSAT law, sorry, what I'm saying, the Ampere's circuital law. So we wrote as mu naught into I enclosed, but this we can rewrite as in terms of current density, because that is written as J dot D. And why this is so? Because J need not to be always uniform over the cross section. So you may get a variable J as well. Okay. So first of all, you need to do the J dot dA over the surface to get the current enclosed, because J is a variable, and then write the Ampere law. So we can do now the next question. Calculation of B inside wire when current density varies over cross section. So let's say if I give you example that J equals to J naught 1 minus R by R, and definitely this is the cross sectional view, it is infinite wire. of radius r, and the r is only inside. So of course this formula is true only when r is less than or equals to r. So the domain actually.
Yes.
And you are supposed to find the b inside and b outside, both. To find b when r is less than r, so try this out.
Yes, sir. Sir, for
Yeah.
R greater than capital R, it will behave like an infinite current carrying wire only, right, sir?
Yeah, and you just need to find the current, the total current.
Yes,
So the boundary ends at r capital R, no? So up to r, whatever is the current is the net current, right?
yes, sir.
So you have to use that current as the I and then solve. For outer point, inside we have variation, right?
Yes, sir.
So for inside we will do the integration from 0 to small r.
Yes, sir.
And I hope if you're doing the same, you will get the right answer.
Okay, sir. So for inside, I'm getting mu naught J naught 1 minus R by 2R.
Not J not equal no. R will also come out. Something else.
Uh,
So when you write the current density into area, the area will be 2 pi r dr, not pi r square. You're finding the current through the cross section which you have drawn at a distance r, right?
Yes, sir. So I made a mistake in this. sir.
Yes. Tell me.
Sir, for R less than capital R, I'm getting mu naught J R 1 by 2 minus R by 3 R, sir.
Not J by 2.
So mu naught J R.
Okay.
And there's, sir, I didn't take the by 2 term.
Mu naught
Okay.
JR.
Yes, sir.
R by 2 minus R square by 2, 3R. What is that? How much you getting?
So 1 by 2 minus R by 3 R.
Okay, 1 by 2. So I think this is correct answer. So you should have written mu naught J R by 2 minus R square by 3R, right?
Yes, sir.
Okay, and you can see it's a quadratic with a coefficient of R square negative, which means it's an inverted parabola. So we
Yes,
can find the maximum. So for B max, dV by dr will be 0.
yes, sir.
So 1 by 2 minus 2R by 3R is 0. So R becomes 3R by 4. So at a 3/4 radius, the B becomes maximum instead of surface, which was the older case. Okay.
Yes, sir.
All right. So we'll now you can start doing other problem, but we'll also continue solving in the next lecture.
Oh,
So today is Sunday, na? So tomorrow we'll cover most part of the impaired law. We'll go for the motion of charge part. So motion is a relatively small topic. It takes maximum of 2 lectures to finish. And after motion, you are done with the first part of magnetism. The other part is called classical magnetism. The classical magnetism is same as electrostatics dipole. Okay. The other part is called magnetic properties of materials. So it is like you have to just read 2-3 pages from S. Verma and you're done. It's pure theoretical. And then we have something called Earth's magnetism, or you can say terrestrial magnetism. So again, it is like a bit of dipole and some extra concept. So you read for one while, then I'll teach you that part. So that is what you will not understand on your own. But it's good to read SC Verma only. No other book is required. Okay. So see you tomorrow.
yes, sir.
Bye. Take care.
Bye, sir. Thank you, sir.
I'll share the sheet and you give me the date for which
Yes.
the sharing is missing.
Okay, sir. I'll share it, sir.